It's a presentation by Chioma Anierobi, who obtained a master's degree from the University of Waterloo and was a researcher at this university. She now moved to the industry. Her work focused on the application of energy storage to defray high peak power electricity prices for commercial and industrial customers in Ontario. So I'll show the video right away.
Hello everyone, my name is Anierobi Chioma. I'm a graduate of University of Waterloo, where I obtained a master's degree in electrical and computer engineering. My research work at Waterloo was supervised by Professors Claudio, Canizares and Kankar, Bhattacharya, and it focused on bill optimization of an industrial customer using behind-the-meter compressed air energy storage. Currently, I work as a power consultant with CPCS Transcom Limited, a management consulting company with head office in Ottawa, Canada, and other offices across the globe. Since joining CPCS, I have been hugely involved in renewable and storage-related assignments with special focus on emerging markets. Today, I'll be presenting our paper titled Behind the Meter Compressed Air Energy Storage, Feasibility and Applications. And my presentation will follow the following outline. I'll start off by speaking on the driving force for this work and the objectives of the research. Then I will touch on the case. When I say case, I mean compressed air energy storage. And then I'll provide insights on the Ontario's electricity market structure. Following that, I'm going to talk about the model we developed and discuss the results of the research outcome. In 2010, the Ontario government introduced what is called Industrial Conservation Initiative, a demand response program aimed at shifting large electricity users' consumption to off-peak hours when the Ontario system is at its highest demand. It allows large customers to manage their global adjustment costs by reducing demand during peak periods. Load management of industrial customers is very challenging. Curtailing production during the system peak hours could save the customer a significant amount of electricity costs, no doubt. The challenge for the customer lies in balancing its monetary gain from load reduction at peak hours vis-a-vis the disruptive effect on its production line. Behind-the-meter energy storage has advantage. It can reduce the industrial customer's power demand from the grid without interrupting its usual daily activities. Small-scale compressed air energy storage is a possible option, especially where there exists an abandoned mine or cavern that can be repurposed for air storage. The question remains on whether it is economically viable. Hence, investigating the feasibility and economic viability of small-scale CAES for an industrial facility with available empty wells for air storage to defray the high peak power electricity prices of Ontario is the focus of this research work. Armed with this motivation, we define our objectives as follows. First, to develop a mathematical model. The optimization model will seek to determine the minimum electricity cost operation, the storage energy management, the storage energy output, and corresponding charging and discharging decisions of the small-scale CAES over the planning horizon. And of course, perform a detailed economic and sensitivity analysis to gain useful insights on the viability of such investment. On this slide, you can see a schematic diagram of CAES. CAES is a type of storage technology that uses off-peak electric energy to compress air and store the compressed high-pressure air in a storage reservoir, which is then released during the peak periods to drive a turbine generator to produce electricity. CAES can use different reservoirs to store the compressed air. Existing underground, salt mine, porous rock, depleted gas field are ideally cost-effective storage medium for CAS. And the diagram on the right-hand side shows a case design based on the compression and air expansion heat management. The DD case is diabetic CAS, and then we have where the heat resulting from compression is not recovered. The adiabatic CAS, the heat is recovered and stored and reused during the expansion process. And then we have the fuel-free CAS or advanced CAS, and of course isothermal compressed energy storage. Ontario electricity customers' bill comprises of two components majorly. The hourly Ontario energy price, which is usually the energy charge component of the bill, and global adjustment demand charge. All customers in Ontario pay global adjustment. How they are billed is determined by the type of customer they are. Customers that participate in the Industrial Conservation Initiative, referred to as Class A customers, usually with average demand of 1 megawatt and above, pay their share of the GA cost based on the percentage their consumption contributes to the top 5 system peaks in a year. All other customers in Ontario pay a share of GA through the Class B GA rate defined by the Independent Electricity System Operator in Ontario. The objective of the proposed small-scale CAS model is to minimize the electricity cost and the CAS system operation cost incurred by the industrial customer. Thus, an optimization problem is formulated considering a given capacity of small-scale CAS and the decision variables are the charging and discharging decisions of the small-scale CAS and the energy purchase consumption schedules of the customer over a given time horizon. On this slide is the cost model that we developed. On the left-hand side of the model is the total annual cost of the customer without CAS, and on the right-hand side of the model is the total cost of the customer with CAS. You can see the GA charge, the energy cost component, the third item and the last item are the variable and fixed operation and maintenance costs respectively. On the bottom is the savings resulting from using CAS, which is determined by CAS cost without CAS minus cost with CAS. This section presents the objective function of a Class A customer with CAS plant installed in the facility to reduce its global adjustment charge. The optimization aims to minimize the total customer annual cost subject to the following model constraints. And on the right-hand side is the flow chart that summarizes the modeling framework to achieve the load reduction for electricity cost savings in an industrial facility using behind-the-meter energy storage. The models developed in the previous 2 slides is applied to a load profile of a real Class A customer in Ontario to determine the possible cost reduction resulting from deploying an SS-CAES system at the customer's facility to reduce the load demand and energy drawn from the grid. I don't know if I've mentioned already, but the reduction in the facility's demand using CAS will not change its global adjustment charge for the current month. For example, a load demand reduction in June of 2017 will reflect in a global adjustment charge for June 2019. Therefore, to capture the overall impact of CAS in details, the electricity charges for the complete IS cycle is considered. Thus, in the base period, the peak demand factor of the customer is determined and then applied in the payment period or adjustment period to determine the monthly GA. of the customer, and that's why we have like 2 years of customer's load profile, 2 years of GA, 2 years of HOP to capture the base period when the peak is measured, and then the adjustment period when the payments will be made. The key findings includes that CAES is able to respond to the model is able to respond to changing electricity prices. You can see it charging at low prices and discharging during high price hours. And of course, we also observe that savings increased with increasing case sizes. A case capacity of 2 megawatts for 2 hours discharge duration and above resulted in savings, and therefore are considered feasible sets for economic analysis. In this slide, we examine the economic feasibility and risk over the long term of a small-scale CAES plant installed at a customer's facility for load management applications. We consider different case sizes, electricity prices, case unit cost, and life cycle for sensitivity analysis to evaluate how the revenue of the investor will be impacted by these changes. The first analysis was like back of the envelope calculation, where we fixed the peak demand of the customer, and then we try to determine the cost for different sizes of CAES. And then to capture the variability in the facility's load profile, we did a detailed economic analysis by simulating the optimal operation of the case for different sizes and life cycles. Small-scale case projects are the development stage. Economic uncertainties are relatively high, and therefore it is necessary to perform a sensitivity analysis to understand the significance of various parameters affecting CAES investment viability. The first of such parameter that we considered is global adjustment. And in this case, we saw that for a case size of 2 megawatts and 2 hours discharge duration time and above, the IRR is greater than 15% for 5% reduction in GA. However, approaching 25% or from 15% reduction in GA, even up to 25% reduction in GA. Case capacity of 3 megawatts by 6 megawatt hour still shows IRR greater than 15% for project life cycle of 25 years and above. Another parameter that we considered in the sensitivity analysis is the case capital cost, due to uncertainty surrounding the cost of CAES, as there are not much of such projects around the world. We started our base case with $2,000 per kilowatt and varied where $2,000 per kilowatt is for a higher capacity case like 10 megawatts, and 3,500 was used for like 1 megawatt case capacity, considering economies of scale. And then we try to vary it by increasing the cost by $500 per kilowatt. And what we observe is that up until 3,000 to 450 megawatts, case capacity of 7 megawatts and 2 hours discharge duration show IRR greater than 15% for project cycle of 30 years and above and beyond. However, going beyond $4,500 shows an IRR that is low, far less than 15%. And we might say that we can conclude that this investment is not worth it. To further understand the impact of the energy capacity of the case plant on the cost reduction, a fixed discharge power duration is considered while increasing the energy capacity. And the results, as you can see on the slide, is shown on the slide. Notice that the energy capacity does not play a significant role in the cost saving. For example, we notice that doubling the energy capacity of the case only increase the capacity by 1.13% annually. And this is because the cost savings are primarily dependent on the global adjustment reduction, which depends on the case power discharge rating. We can conclude that behind the meter energy storage is economically viable in Ontario. Large discharge power is better than energy capacity. Capital cost and GA are the most influential parameters. Going forward, it will be nice to look at the stack services that the behind the meter case can provide. And of course, compare case with other load management technologies like PV. It will be interesting to investigate the
Okay. Chioma, you're back. Yes, you're here. You can unmute your microphone, maybe.
Sure.
Yeah. Thank you. So please, from the floor, if you have any question, feel free to ask. I was a bit, I will maybe ask a quick question or two. I was a bit surprised by the high costs of compressed energy storage. Did you compare it to lithium-ion batteries or to other type of storage?
Well, this work was based on consultation with developers of this technology. In fact, it was actually based on an existing project that was being done at that point. They were building a project of similar capacity, so all the costs that we used for this analysis was based on what they provided.
Okay. You made a sensitivity analysis on several energy versus power ratio in your analysis, I think, in your paper. Wasn't it possible, or wouldn't it be possible to size it simultaneously and try to co-optimize the size and the energy of the storage system?
Yeah, this pricing model in Ontario specifically depends on the power. Depends on the power more than on the energy capacity of the storage system, because you're targeting like 1 hour, and then you're looking at like 5 hours in a year. So most times you don't have to like have a storage with so much energy capacity. You don't really need that because you are targeting one particular hour in a day.
Okay.
So I don't know if that makes sense. Like, it's based on your peak demand, not necessarily how long the peak lasted.
Okay, thank you. I don't know if anyone else has a question. Maybe a last quick question. So you mentioned the 5, I don't know how you call that, the 5 peak hours?
Yes.
So they are known, you assume they are always known in advance? Is it fixed, or normally is it something that that is just known after the fact?
Yeah, it's something you know after it has happened. Okay, so but there are like the system operators usually provide forecasting of the system peak when it is expected to occur. And there are also service providers who have like special algorithm to track the system peak. So as a customer, you can go into contract with them to sort of alert you that the peak is going to occur, say 4 p.m. today. So do whatever you need to do to keep your peak low. Yeah, so it's not, you don't know ahead of time, but there are ways to forecast the peak.
Okay, thank you. So if there is no other question or comment, thank you, thanks a lot, all the presenters for these nice presentations, and I will now conclude the session, and Well, see you tomorrow.